Now let us continue with the equations of motion using graphical method. Newton studied motion of an object and gave a set of three equations of motion. These relate the displacement, velocity, acceleration and time of an object moving along a straight line. Suppose an object is in motion along a straight line with initial velocity u. It attains a final velocity v in time t due to acceleration a. Its displacement is s. The three equations of motion can be written as v is equal to u plus at. This is the relation between velocity and time. S is equal to ut plus half at square. This is the relation between displacement and time. V square is equal to u square plus 2as. This is the relation between displacement and velocity. Let us try to obtain these equations by using graphical method. First one, equation describing the relationship between velocity and time. Figure 1.9 shows the change in the velocity with time of a uniformly accelerated object. The object starts from d in the graph with velocity u. Its velocity keeps on increasing. After time t, it reaches a point B on the graph. The initial velocity of the object u is equal to OD. The final velocity of the object v is equal to OC. Time t is equal to OE. Acceleration is equal to change in velocity upon time. So acceleration is equal to final velocity minus initial velocity upon time. That is equal to OC minus OD. Therefore, CD is equal to AT, equation 1, since OC minus OD is equal to CD. Draw a line parallel to y-axis passing through B. This will cross the x-axis in E. Draw a line parallel to x-axis passing through D. This will be cross the line BE at A. From the graph, BE is equal to AB plus AE. Therefore, V is equal to CD plus OD, because CD is equal to AB is equal to CD and AE is equal to OD. Therefore, V is equal to AT plus U from equation 1. Therefore, V is equal to U plus AT. This is the first equation of motion. Students, you have to practice derivation of this equation and you need to learn also this. Now, second equation. The second equation describes the relation between displacement and time. Let us suppose that an object in uniform acceleration A and it has covered the distance s within time t. From the graph in figure 1.9, the distance covered by the object during time t is given by the area of the quadrangle DOEB. I hope you can see DOEB. Now, therefore, S is equal to area of quadrangle DOEB. That is equal to area of rectangle DOEA plus area of triangle DAB. Therefore, S is equal to AE into OE plus half into AB into DA. But AE is equal to U, OE is equal to T, and OE is equal to DA equal to T. AB is equal to AT because AB is equal to CD from equation 1. Thus, we can say that S is equal to U into T plus half into AT into T. Here, U is AE, T is OE, AT is AB and T is DA. Therefore, Newton's second equation of motion is S is equal to UT plus half AT square. So, derive this equation also, practice it. Next, let us go to the third equation describing the relation between displacement and velocity. We have seen that from the graph in the figure 1.9, we can determine the distance covered by an object in time t from the area of the quadrangle DOEB. DOEB is a trapezium, so we can use the formula for its area. So therefore, S is equal to area of trapezium DOEB. That is equal to half into sum of the lengths of the parallel sides into distance between the parallel sides. So S is equal to half into OD plus BE, sum of the lengths of parallel sides, into OE, distance between parallel sides. But OD is equal to U, BE is equal to V, and OE is equal to T. Therefore, S is equal to half into U plus V into T. So second equation here. But A is equal to V minus U upon T. So rearranging this, T is equal to V minus U upon A. Third equation. Thus, we can say S is equal to half into U plus V into V minus U upon A. Now rearranging this, S is equal to V plus U into V minus U upon 2A. 2 into A is 2A. So again rearranging, therefore 2AS is equal to V plus U into V minus U, that is equal to V square minus U square. You know that A plus B into A minus B is equal to A square minus B square. Similarly here, V plus U into V minus U is equal to V square minus U square. Therefore, V square is equal to U square plus 2AS. Rearranging them, this is Newton's third equation of motion. So, you have to learn and practice lots to derive these equations. Now, let us go to always remember the velocity of the accelerated object changes with time. Change in the velocity can be due to the change in direction or magnitude of the velocity or both. So I hope you have understood these equations. Now let us go to the next concept, uniform circular motion. Observe the tip of the second hand of a clock. What can you say about the velocity and the speed? The speed of the tip is constant, but the direction of its displacement and therefore its velocity is constantly changing. As the tip is moving along the circular path, its motion is called as uniform circular motion. Can you give some more examples of such motion? Okay, let's see now. Here, try out and think about it. Let's see. First one, draw a rectangular path as shown in figure 1.10. Place the tip of your pencil on the middle of any of the square path and trace the path. Note how many times have you to change the direction while tracing the complete path. Now repeat this action for pentagonal, hexagonal, octagonal path and note the number of times you have to change the direction. Fifth, if you increase the number of sides of the polygon and make it infinite, how many times will you have to change the direction? And what will be the shape of the path? So this shows that as we increase the number of sides, we have to keep changing the direction more and more times. And when we increase the number of sides to infinity, the polygon becomes a circle. So we have to change the direction infinite number of times. When an object is moving with a constant speed along a circular path, the change in velocity is only due to the direction, change in direction. Hence, it is accelerated motion. So, when an object moves with constant speed along a circular path, the motion is called uniform circular motion. You can mark this definition. Example, the motion of a stone in a sling or that of any point on a bicycle wheel when they are in uniform motion. Now, if an object moving along a circular path of radius r takes time t to come back to its starting position, its speed can be determined using the formula given below. Speed is equal to circumference upon time. So V is equal to 2 pi r. Circumference is represented by 2 pi r upon t, where r is the radius of the circle. So find more examples of circular motion in your day-to-day life. So we can say pulley, wheel of the cycle, motion of the fan, etc. Now in this figure you can see the earth is having circular motion, and similarly here also you can say in this circle this is the needle of the clock, you can say, and it is also moving with circular motion. Now let us go further to determine the velocity of uniform circular motion. Now let's try this. Take a circular disc and put a 5 rupee coin at a point along its edge. Make it move along its axis by putting a pin through it. When the disc is moved at higher speed, the coin will be thrown off as shown in the figure 1.11. Note the direction in which it is thrown off. Repeat the action, placing the coin at different points along the edge of the circle, and observe the direction in which the coin is thrown off. Now, you can see here further on the next page, the coin will be thrown off in the direction of the tangent which is perpendicular to the radius of the disc. Thus, the direction in which it gets thrown off depends on its position at the moment of getting thrown off. It means that as the coin moves along a circular path, the direction of its motion is changing at every point. So I hope you have understood this concept of uniform circular motion. Now let us see the solved examples. An athlete is running on a circular track. He runs a distance of 400 meters in 25 seconds before returning to his original position. What is his average speed and velocity? So given total distance travelled is equal to 400 meters. Total displacement is 0 as he returns to his original position. Total time is 25 seconds. Average speed you have to find out. Average velocity also we have to find out. So average speed is equal to total distance covered upon total time taken. That is equal to 400 upon 25 is equal to 16 meters per second. Average velocity is equal to total displacement upon total time taken. So total displacement is 0 upon 25, that is equal to 0 meters per second. Now let us go to the second example. An aeroplane taxis on the runway for 30 seconds with an acceleration of 3.2 meters per second square before taking off. How much distance would it have covered on the runway? So here it's given that acceleration is 3.2 meters per second square. T is equal to 30 seconds. We have to find out S. U is equal to 0. So by using the second equation which shows the relation between displacement and time. So S is equal to ut plus half at square, that is equal to 0. U is 0. So 0 into 30 plus half into 3.2 into 30 square. So 0 into 30 is 0. So your 2 ones are and 2 1.6, that is 16s are cancels, and therefore 300 square is 900, 30 square is 900. So 1.6 into 900 you get 1440 meters. Okay. So this much distance it is covered on the runway. Now see the third example. A kangaroo can jump 2.5 meters vertically. What must be the initial velocity of the kangaroo? Acceleration, you know, it is 9.8 meters per second square. S is equal to 2.5 meters. It is jumping 2.5 meters up vertically. V is equal to 0. We have to find out initial velocity U. So we'll use the relationship between displacement and velocity. The equation given is V square is equal to U square plus 2AS. So V square is 0. That is equal to U square plus 2 into 9.8 into 2.5. Negative sign is used as the acceleration is in the direction opposite to that of the velocity. It is jumping up. So it's going in the opposite direction. So 0 is equal to U square minus 49. So U square is equal to 49. U is equal to 7 meters per second. Fourth example. A motorboat starts from rest and moves with uniform acceleration. If it attains a velocity of 15 meters per second, per second in 5 seconds, calculate the acceleration and the distance travelled in that time. Initial velocity u is equal to 0. Final velocity v is equal to 15 meters per second. Time t is 5 seconds. We have to find out acceleration. From the first equation of motion, a is equal to v minus u upon t, that is equal to 15 minus 0 upon 5, that is equal to 3 meters per second square. Now, from the second equation of motion, the distance covered will be s is equal to ut plus half at square. So s is equal to 0 into 5, that is 0, plus half into 3 into 5 square. So 0 plus 25 into 3 is 75 upon 2, that is equal to 37.5 meters.